Thwaites has earned the moniker Doomsday Glacier.
It's the largest, most menacing source of rising sea levels all over the world.
It's already dumping 50 billion tons of ice into the ocean each year.
They estimate the ice shelf on Antarctica's massive Thwaites Glacier could collapse within the next 5 years, causing a dramatic sea level rise.
They're calling it the Doomsday Glacier.
Hi, I'm Mikhail Thompson, and I'm studying architecture at Washington University in St. Louis. I'm going to be your climate host today as we investigate the stability of Thwaites Glacier in Antarctica. It's a glacier commonly referred to in the news as the Doomsday Glacier. You might be wondering why a future architect in Missouri is worried about a glacier all the way down in Antarctica. Let me explain. Thwaites got its name, the Doomsday Glacier, because scientists believe that it has the potential to rapidly speed up the current rate of sea level rise. Rapidly rising sea levels would displace millions of people, cause mass suffering, mass migration, and huge economic damage. If sea levels rise just 1 to 2 feet more in my career, millions of people and businesses across the planet will need to rebuild or modify their current coastal locations and rebuild on higher ground. Sounds like job security for an architect like myself. So let's get this series started. Throughout this virtual field lab, we'll be taking measurements on and around Thwaites Glacier. Measurements that are like checking the vital signs of a person you might think is sick. Let me pass you on to Karen and Richard Alley, a father and daughter science team that have spent their lives collecting data on and around Thwaites. They should be able to tell us if this glacier really deserves to be called the Doomsday Glacier.
Thanks, Mikhail. My name is Karen Alley, and I'm standing on the southern edge of Ellesmere Island next to a piece of sea ice that froze out of seawater and then was washed up on shore here. I spend most of my time, though, studying land ice, such as glaciers and ice sheets, including Thwaites Glacier, which is what we're going to get into in this series. I live in Winnipeg in Canada with my husband and 2 cats, but I also spend a lot of time in the States where I grew up and where both my parents still live. You might wonder how I got into glaciology. Well, my dad had a lot to do with that. I swore all my life I'd never go into his field, but it turns out he's the most enthusiastic scientist that I've ever met, and it's hard not to get excited about what he does. I'm excited for you to meet him now.
And I'm Karen's dad, Richard Alley. I teach at Penn State. I'm married to her mother, Cindy, who was a geologist who studied ice and now teaches quilting. Our other daughter, Janet, Karen's sister, is a brilliant science teacher. I first went to Antarctica in 1978 as a sophomore at Ohio State. I've been back 3 times, 9 times to Greenland, several times to Alaska to work on glaciers, and to other parts of the world to work on glaciers. I've had the amazing opportunity to study ice with Karen. We do study the ice, but we also study the history of the ice and what it does. And so that's why we're here in the Cleveland Metro Parks, because during the Ice Age, right out there was a giant glacier, a little bit like Thwaites Glacier, that was carving Lake Erie. That glacier then melted away as the Ice Age ended, in part because of rising carbon dioxide in the atmosphere, and that water went into the ocean to raise sea level. We humans are now raising carbon dioxide in the atmosphere, warming the world and melting the ice much faster than nature did when it ended the Ice Age, in large part by burning fossil fuels and releasing the CO2 to the air. And we're especially worried about Thwaites Glacier because it's the place that is most able to supply a lot of water to raise the ocean in a hurry. Thwaites is what we call an outlet glacier because it lets ice flow out into the ocean from the 2-mile thick pile that is the Antarctic ice sheet. Ice sheets form when old snow accumulates faster than it melts, and it's squeezed to ice as more snow falls on top. Ice sheets spread under their own weight, like pancake batter poured on a waffle iron. When the ice gets about 100 meters thick, a bit over 300 feet, this spreading is fast enough to be called a glacier or an ice sheet. The ice on Antarctica has been building up and flowing out for millions of years, although the oldest ice has melted off the bottom or flowed out to the ocean already. some of the ice flowing out of Thwaites Glacier into the ocean is still more than 20,000 years old.
Here's a simplified cross-section that shows the West Antarctic ice sheet and the Thwaites Outlet Glacier. Thwaites Glacier has all the characteristics that make it a potential game changer when it comes to future sea level rise. First of all, it's huge. There's ice upstream. You can kind of think of that as a reloading zone that's flowing down to the ocean and then ends up in the ocean influencing sea level rise. And the ice in Thwaites Glacier has the potential to raise sea levels around the world by 65 centimeters, which is over 2 feet. The first spot that we need to pay attention to is called the grounding line. Most of Thwaites Glacier is sitting on land, but at some point it reaches a spot where it goes from sitting on land to floating, and that spot is called the grounding line. Thwaites' grounding line is retreating, so we have to keep a close eye on the changes there. The second place in contact with the ocean on Thwaites that we need to keep an eye on is a floating ice shelf. As ice flows from the upstream reloading zone and crosses the grounding line, it goes afloat. There's a whole area of the Thwaites Glacier that's actually floating on the ocean, even though it's still attached to the ice upstream. So one of the vital signs that we keep a close eye on is the health of this ice shelf by looking at things like the size of the ice shelf and the velocity or the speed of the ice flow across the ice shelf. The third spot that we need to keep a close eye on is called a pinning point. So on the Thwaites ice shelf, after it flows across the ocean for a bit, it actually runs aground again. And that spot where it runs aground again is called a pinning point. And we can watch the interactions between that pinning point and the ice shelf to understand if the ice shelf is likely to stay stable in the future. One important vital sign of glacier health is the ice flow speed. Sometimes glaciers, particularly those that are in contact with the ocean, will speed up a lot when they're going through a process that's destabilizing them. So let's look at the ice flow speed on the Thwaites eastern ice shelf to understand how the stability of Thwaites Glacier might be changing. In your notebooks, I want you to write down this question. What does the speed of the Thwaites eastern ice shelf over the last 20 years tell us about the stability of Thwaites Glacier? Now I'm going to turn it over to some young scientists from Sacramento who will take you through the data collection process.
Hello everybody, my name is Evelina Chang.
My name is Sarah Gomez.
And my name is Haley Love. And we are all seniors attending Grant Union High School in Sacramento, California. And we all plan to study in different fields of science in college next year.
Karen and Richard have asked us to help analyze the speed of Thwaites Glacier over the past 20 years.
That should be no problem. Let's start by getting familiar with what the satellite image of Thwaites looks like. Here's a cross-section sideways view of Thwaites that you saw earlier. The satellite gives a view from above rather than from the side. Here's the same general area seen by the satellite, as well as a flyover of the actual area being studied.
This red line shows the shoreline where the glacier flows off the land and onto the ocean. The grounding line would be right under this part of the glacier. The little red circles are actually the underwater islands that are acting as pinning points. These pinning points help slow down the flow of the glacier.
Between the offshore islands and the coast of Antarctica is the Thwaites eastern ice shelf. This is the huge mass of floating ice that holds back the western Antarctic ice sheet. Hopefully now you're able to look at any of these digital images and get a good mental picture of what the Thwaites Glacier looks like. Here is how we are going to measure the speed of the glacier over the past 20 years. We have different satellite images of Thwaites that show how fast the glacier is actually flowing. Some parts of the glacier move faster than others. The different colors show the different flow rates.
The scale on the side is the key showing the speed of the glacier. Anywhere you see purple, the glacier is moving slowly. Anywhere you see yellow, the ice is moving much faster, as fast as 3 meters every day.
Since this is a really large area, we need to pick a constant spot to measure the speed. We'll use this box as a constant location to measure our speed. Let me show you how I would make the first couple of measurements. Then I will turn it over to you. If I look at the colors in the testing area and compare it to the scale, I would estimate the flow of the glacier in 2002 to be about 2.3 meters per day. This is not an exact science, so your answer may be a little different.
Let's make a data table in your notebook to record this data. On the left, we'll put the year. On the right, we'll put the flow rate. Let's enter the flow rate for 2002.
Next, I'll bring up satellite photos for each year in your data table. When you're done measuring all 8 satellite photos, we'll talk about how to turn the data into a graph.
Welcome back, and nice job making all those measurements. I don't know about you, but I found some of the years harder than others to make a good estimate. Here are the measurements that I made for each year. Hopefully our data are at least close to each other. Next, I think it would be best to put these data onto a graph. Oftentimes, a graph helps to tell the story of the data better than simply looking at the numbers on a table.
Let's make a graph in your notebook. We can put the speed on the y-axis and the years on the x-axis. Pause the video while you build your own graph. Make sure to include a trend line that shows what has happened to the speed of the glacier over the past 20 years. When you are done, hit play again and we can see how our graphs compare. Welcome back. Let me bring up my graph and we'll see how our data compares.
The best fit line was tough to draw on this graph. But if I look at the story the data is telling, I think the best way to draw it would look something like this. Between 2002 and 2006, it seemed like the flow rate of the glacier was speeding up. Since 2008, it seems like it's been gradually speeding up again. Faster flow rates indicate the glacier is losing stability. Let's add notes onto your graph that show where the data suggests the glacier is becoming more unstable.
Let's take one more pause and do a little data analysis. In your notebook, write down 2 things you noticed and 1 thing you wonder about the data and graph. When you're done, hit play again and we'll turn this back over to Karen and Richard to see what they think of our data.
Welcome back. When I started researching the Thwaites Eastern Ice Shelf, I hypothesized that we would see kind of a steady increase in ice flow speed as the ice shelf responded to a warming ocean. I was really surprised to see the graph that we got. One thing I noticed was that there was a big increase in speed early in the record, and then somewhere around the year 2008, there was a sudden decrease in the speed of the ice shelf. Another thing I noticed is that after that big decrease in speed, we do see a pretty steady rise in the ice flow speed up to the present day.
When we scientists get data like this, we get really excited because there must be an important story to explain what none of us saw coming. Someone may look at the data and say, it all looks good. The speed is down, so there must be less ice flowing into the ocean. This is where you really need to step back and look at the bigger picture. Turns out, the speed at the mid-shelf location dropped because within only 2 years, the entire western ice shelf broke apart. Look at these images of the western ice shelf during that time. The entire shelf catastrophically disintegrated. The faster-flowing western shelf had been dragging the eastern shelf along with it. When the western shelf broke up, it let go of the eastern shelf, which then slowed down. But since then, the eastern shelf and the ice flowing into it have been speeding up again on their own. And in addition to this extra flow into the eastern ice shelf, the ice flowing off the ice sheet into where the western ice shelf used to be has also sped up. Looking at more of the data gives us the bigger picture. Thanks for going on this journey with us to collect vital signs on Thwaites, the Doomsday Glacier. Our first vital sign, the speed of the glacier, seems to indicate that the stability of Thwaites is changing, and not changing in a good way. The speed of the glacier is only one vital sign. To find out if this glacier is really a threat to humanity and deserving of the Doomsday Glacier name, we should probably go back and analyze some additional vital signs of the ice shelf and pinning points that are still holding the glacier back. That will give us more insight into the stability of the glacier and its potential to cause rapidly rising sea levels around the world. See you in episode 2.
Thanks for
Okay, now I think we should just do it ever after.
Yeah. Thanks for doing science with us.
Oh, no,
Thanks for doing science with us.